Okay, so in this video, we're going to talk about graphing absolute value inequalities. And what does that mean? So we're going to eventually get to actually graphing absolute value inequalities, and on a graph, it's going to look something like that. But first, I want to go over some of the foundations. When we are graphing inequalities like x is greater than 5, we know how to do this. We've done this for so long at this point. We know that you are going to go to, right? So we have 0, 1, 2, 3, 4, and 5, and then we have all the rest of the numbers, right? And what we do here is has one variable in it, right? Which is why it is on a number line. This is a one-dimensional graph. And so we go to 5, we do an open circle on 5 because it is not including 5, and we go to the right. The reason we know we go to the right is because basically what are we shading? We are shading what is called the solution set. What does that mean? It means that everything that's shaded satisfies this inequality, right? So, for example, 6 is greater than 5. It checks out, right? 100, right, is greater than 5. It checks out. It is an open circle because 5 is greater than 5 is not a true statement. Okay, so that is why we do not write, that's why we have an open circle on 5. And then everything that's not shaded in, so all of this, does not satisfy our equation, right? 4 is greater than 5 is not true. 4 is greater than 5, not true. I know this is pretty basic, but it's going to apply. Now, we're going to take that and we move that into 2 dimensions, right? So the reason it's 2-dimensional is because we have a y and an x. 2 variables means 2 dimensions, okay? So now we have this and we need to find the solution set of all points, right, x and y, that satisfy this equation or inequality. Same concept. We just did that above with 1 variable. Now we're doing it with 2 because we have x and y. 2 dimensions. So now, don't worry, we're not going to get into 3 dimensions, not just yet. So, what do we do here? There are 4 main steps in doing this. 1, you're going to graph or plot, let's say plot the points. We know how to graph a line. Plot the points. This is just, we're doing a line to warm ourselves up into this. So we go up 1, right? That's our y-intercept, and then we have a slope of 3, up 3 over 1, and then I'm going to go the other way for accuracy. So instead of up and right, we're going to go down and left. 1, 2, 3, and left. 1, 2, 3, and left. Okay? Now, second, we're not going to draw the line just yet. You know how here, when we did it, we found the value, which was 5, and then we have to ask ourselves, is it open circle or closed circle? Same thing, except instead of open circle, closed circle, we're going to ask ourselves, is it solid or dotted? Solid or dotted line, okay? It is solid when it is less than or equal to or greater than or equal to. It is dotted when it is less than or greater than. So what is it going to be? Well, it is going to be this is greater than, so that tells me immediately that it is going to be, just like it would be an open circle, it is going to be a dotted line. So I'm going to take this and I'm going to dot it. And we'll talk about what that actually means after we're done. And then 3 is going to be 2. We have to shade, right? The same way, again, here we shaded. But we need to shade one way or the other. But in order to know that, we're going to test a point. Now, here's what you want to catch. It is either going to be, just like on a number line. If I have a number line and I'm shading an inequality. And I have a point, right? It is either going to be everything to the right or everything to the left. It is not going to be both, and it is not going to be some here and some here, right? If we are dealing with one inequality, not a compound inequality. So we have to test, is it going to be all of this or is it going to be all of this? It's one or the other. It is either going this way, or this way. It is not going to be both. It is not going to be something over here and something over here. No. It is going to be all or none. Okay? So, test a point. I'm going to test a point to see if it is in my solution set. Again, we are looking for the solution set that of all the points that satisfy this inequality. Meaning, if I test a point, which the easiest point to test is 0, 0. The only time you cannot test 0, 0 is if it is on your line, but it's not. So I'm going to test a point. For example, like this one, 0, 0. So I'm going to plug it in. So I have 0 is greater than 3 times 0 plus 1. I'm testing a point. Okay, so I test it. So I get 0 is greater than, this goes away, 1. Is 0 greater than 1? Is this true? No, this is false. I'm going to write this down. False. So that means that this point, 0, 0, is not in my solution set. Meaning the rest of the points on this side are not in my solution set. So what does that mean is in my solution set? The other side of the graph. So I'm going to shade the other side of the graph. So fourth step is to shade. So again, you are testing a point to see, is it in your solution set? If it is, you shade towards the point. If it is not, you shade away from the point. So what does this tell me? This tells me that all of these points right here in this blue area, plus, that's it, just the blue area is in my solution set. Now, the points on the line do not satisfy my equation because it is a dotted line. Just like an open circle does not satisfy it, a dotted line does not satisfy the equation. So let's look at what that would look like if it was an absolute value equation. Same steps. Graph it or plot the points. Let's write it like that. Plot the points. Dotted or solid. Test a point to see if it's in the solution set. Shade. Okay, so let's do it. So we have this function right here. F of x equals, f of x is greater than or equal to x minus 2 minus 1. The absolute value of x minus 2 minus 1. So my vertex is going to be 2, negative 1, right? So 2, negative 1. That's my vertex. And then my a value hasn't changed, so I know it's concave up and it's a slope of 1. So my actual shape of my graph is the exact same. So I'm going to go by a slope of 1 and negative 1. Now, is it a dotted or a solid line? Well, it is a solid line because it is greater than or equal to. And then I'm going to test a point. Now, is 0, 0 on my graph? No. So I can test 0, 0. Let's test it. So I have y is greater than or equal to absolute value of x minus 2 minus 1. Plug 0 in. 0 minus 2 minus 1. So I have 0 is greater than or equal to the absolute value of negative 2 minus 1. 0 is greater than or equal to 2 minus 1. 0 is greater than or equal to 1. Is that true? No, not true. So that means I don't shade towards the point. I shade away from it. Now, with absolute value functions and quadratics, but we're not doing quadratics until later, you are either going to shade inside the V or outside the V. So it's either going to look like this right? And I always shade with lines because when we do systems, it looks nicer. Or it's going to look like this, everything else outside of it. So just a heads up that it's going to be everything inside or it's going to be everything outside of the V. And there's your solution set. And last, but most definitely not least, let's do one more problem. And this is also helping us practice graphing our absolute value functions. So if I were you, I would pause this video and I would graph this, just to make sure your graphing is on point. So step one is to graph it. What is my vertex? My vertex is 0, 5. It didn't go right or left and it went up 5. So 0, 5. Now our A value is negative 2/3, which means that it is concave down with a slope of 2/3, right? So I'm going to go down 2, right 3, and down 2, left 3. I'm going to do one more, again, for accuracy. Now, is it dotted or solid? It is dotted, so I'm going to dot it. Now again, with our shading, it's either going to be everything inside or it's going to be everything outside. So let's test it. I'm going to test 0, 0 because it's not on my graph. So 0 is less than negative 2/3, absolute value of 0 plus 5. This is out because it's times 0. So 0 is less than 5. Is that true? Yes. So I shade, because it's part of my solution set, that means all of this is part of my solution set. So I shade everything inside of the V of the absolute value function. And I always make sure that they are approaching it because it's everything from this infinitely. Now, keep in mind, for this function right here, the actual points on the absolute value function, on the V itself, are not part of my solution set, but everything in the green is. Versus this one, it's everything shaded plus the actual function itself because it is solid.